Chapter 6 is all about wind and pressure. The two cannot be separated. They are completely intertwined. Here is why. I have a balloon. Okay, the air rushes outside of the balloon. Why does the air rush outside the balloon? By the way, that's called wind. Anytime the air is moving, it's wind. So why does the air rush out? Why does the balloon produce wind? If I fill up the balloon with air, the pressure inside the balloon is now greater than outside the balloon. Air rushes from high pressure to low pressure. That is the important fundamental concept to understand in the creation of wind. Air goes from high pressure to low pressure. We're going to do a little demonstration here to try and illustrate why the wind blows. So remember, the wind blows because air moves from high pressure to low pressure. High pressure inside, low pressure outside causes the air to move outside of the balloon, and that's what causes to create that wind. In the context of the atmosphere, we need to understand why that's happening. Why does the atmosphere always have wind blowing? Why is it always in existence? We're going to return to the slinky in order to do this. First thing we need to understand is density of air is dependent on temperature. Warmer air is less dense than cold air. So a warm atmosphere, say over the equator near the tropics, is going to be much less dense and therefore expand much more in the vertical than an area over the poles. So that's going to be a lot dense, and the atmosphere is going to be a lot more shallow. It's going to have the same amount of mass, but it's just shallower than it would be over the tropics. That being said, that is what causes the wind to blow. So here, I've got two slinkies. We're going to make the green one the pole, the cold atmosphere. We're going to make the red one the warm atmosphere. Now, first thing I'm going to show you is that on these slinkies, there are two pieces of paper on each one, and they are equally spaced. The slinky represents the entire atmosphere. Remember it from earlier analogies. So this is my entire atmosphere. So there is equal amounts of atmosphere between each one of the papers on both slinkies. Alright, we're going to set these up. And because the cold one is going to be more dense, the atmosphere is not going to expand quite as much. So we're going to hook up our atmosphere here. Okay, there is our cold atmosphere. The warm one is going to be much less dense, so it's going to expand a lot more, and it is going to expand to a higher height. And there is our tropical, or there is our warm atmosphere. Now, something you should notice right away. The slinkies have the exact same number of slinky rings in them, both. But the red one expands much more, which causes those papers to expand much farther than the other ones. At the surface, at the table here, there's the same number of slinky strands under both slinkies. So there's still the same amount of weight, or the pressure here at the table is the same for both atmospheres. It's about 1,000 millibars. But the farther up you go, that changes. Remember, the important thing to remember here is the wind blows because pressure differences at the same altitude. So at the surface, there's not a whole lot of wind that's blowing, probably none at all, because there's no pressure difference between the warm atmosphere and the cold atmosphere. But as we climb up, look what happens. If I take my little altitude reading here, I go up to my first paper, where is here compared to here, look how much higher that same pressure surface, that same amount of mass, is much higher in the case of the warm than it is in the cold. Because there is much more mass here over that same altitude, the pressure is higher at this altitude. Because the pressure is higher here, the wind blows that direction. If I go up even higher, the pressure difference increases even more. If I go all the way up to the top here, look, the entire atmosphere is below this point over the cold one, but not over the warm one. So this is basically 0 millibars. There's no atmosphere above here, but here we still got 100, 200, 300 millibars of pressure still above this point. So here the winds are going to be really, really strong. It goes from basically no pressure difference to an extreme pressure difference because of the way the hot atmosphere versus the cold atmosphere. That is what causes the winds to blow, and that's why we get the jet stream. The jet stream blows much faster at higher elevations because the pressure difference increases with increasing elevation above the ground. So the main points I want you to take away here is the wind blows because of pressure differences. Okay, case one. The reason we have the jet streams, the reason the Earth always has winds, is because the warmer parts of the Earth, and basically near the equator, expand much, much more, which causes these pressure surfaces, these pieces of paper, to expand more, and causes the pressure to be higher than it would be at the same level at the cold atmosphere. So that if the world weren't spinning, the wind would blow directly from the equator towards the North Pole. So that, in a nutshell, is why the Earth has winds, and why we see the fastest winds aloft, and why the jet stream exists. Chapter 6 also introduces pressure systems. It's best to simplify this and don't overthink it. So low pressure systems are associated with rain, thunderstorms, unsettled weather. High pressure systems are associated with fair weather, sunny skies. The reasons for this are low pressure systems have rising motion, and if you remember, rising motion is associated with, or can cause clouds to form. So low pressure systems create clouds. High pressure systems are associated with subsidence, which is just sinking motion, and sinking motion, anytime you have sinking motion, even just a little bit in the atmosphere, it often will kill clouds. So keep those separate: low pressure, unsettled; high pressure, fair weather. In terms of a rotation, we're talking about large scale, so like state to half of a continent size scale here. Low pressure systems in the northern hemisphere rotate counterclockwise. High pressure systems rotate clockwise. Best just to remember and memorize the northern hemisphere, because if you remember that for the northern hemisphere, all you have to do is remember that it's just the opposite in the southern hemisphere. So just remember, northern hemisphere, counterclockwise low pressure, clockwise high pressure. Maybe you make a trick for yourself. High pressure, oh, that's the correct weather, so the clock spins the right way. Something like that. That would work just fine. So that becomes important when we talk about what weather to expect based on the winds, because of the way those pressure systems rotate. The wind will tell you what kind of weather to expect. So let's forecast the weather. How do I do that? Basically, you can just look at the wind direction. If the wind is coming from the south, it generally is a warmer wind, at least in the United States we're talking about here, okay? So in the northern hemisphere, a southerly wind is typically warm. Why? Because the warmer parts of the world in the northern hemisphere are always to the south, towards the equator. Think like if I lived in Missouri, I go to Florida because it's nice and warm. Okay? It's the same thinking. You go south in the wintertime. If you have a north wind, it's the opposite. Since the colder regions are to the north, if you have a north wind, you typically bring in cooler weather. So we can start forecasting here just based off of the wind direction. Second thing is, if the wind direction is coming off of a moist area, say the ocean, you can expect dew points to start going up. And your moisture content, the humidity levels, will start increasing typically. This is most often the case in off of warm bodies of water, like the Gulf of Mexico. So if you have a southerly wind coming from the Gulf of Mexico, you can bet it's going to be warm and humid. All right, that being said, put that in context of low pressure systems and high pressure systems. Low pressure systems rotate counterclockwise. So if you picture a counterclockwise rotation, if you're east of the low pressure systems, the wind is coming from the south, so you can expect warm and humid conditions. If you're west of the low pressure system, since it's rotating counterclockwise, can I do this backwards on the screen here? Yeah, counterclockwise. So on the western side, the winds are coming from the north, and they are therefore going to be usually cooler and drier. And then, the opposite is the case for high pressure systems. The southerly winds are on the western side, and the northerly winds are on the eastern side. So pretty cool how that fits together.